Okay, hello and good morning everyone. Welcome back to Chemistry 3120. JP here. We're going to continue our discussion on the Michael reaction. And what I'm going to do, or at least try to do, is I think I'm going to combine the soft versus hard and specific enol equivalents together. They are actually very much related. So let's focus on that. So last lecture was lecture 24, so this will be lecture 25. So we'll call this soft versus hard. And specific enol equivalents with the Michael reaction. Okay, so before we do that, let's actually go through some examples of the Michael reaction. We discussed a lot about thermodynamics and energetics last class, so let's put that to good practice. So let's predict the products for the following reactions. So if we treat this with LDA and then do a water workup step, what is the reaction what's the product gonna be? So LDA, as you know, removes acidic protons. The only acidic protons you have are here. So you can imagine that you're gonna form an enolate at this position here, and then we wanna set this up for potentially a Michael reaction. So you can imagine this negative carbanion as an enolate could come and it could attack here, or it could also attack this position here, right? So you have potentially a 1, 2, 3, 4, 5, 6, 7 membered ring versus a 1, 2, 3, 4, 5 membered ring. Now, 5 membered rings are much better than 7 membered rings. So the Michael reaction will be the dominant product. Furthermore, you also learn strategies to promote the Michael reaction, and this would include things like decreasing the electrophilicity at the carbonyl. So here you have a very stable non-electrophilic amide, so that further prevents this 7-membered ring from forming. Recall from last lecture, things like aldehydes and ketones would be very susceptible to 1,2 direct addition. So it looks like this would be our product with a 5-membered ring Michael reaction. So what that will look like is you close that 5-membered rings, you have your ester, so this is your new carbon-carbon bond. And there's your amide. Okay, so let's look at another example. If we treat this compound with potassium carbonate is a weak non-nucleophilic base, a reversible base. And we do this in ethanol solvent. What is the product going to be? So again, let's look for potential acidic protons. So we have a set here. We also have a set over here. We have a set over here. Now the most acidic protons are which ones? The most acidic protons are the ones that are between these two carbonyl groups. You can see here that these ones are going to be much lower because you can resonance stabilize the negative charge through both of these carbonyls. So this will be the carbanion that forms. So when that forms, now we look for potential favorable ring formation. So if this comes and reacts, you have a potential 1, 2, 3, 4, 5-membered ring. Okay, if you have this react over here, you have a 1, 2, 3, 4, 5, 6-membered ring, but you can see that it's going to be this unfavorable bridge complex. So the better ring is going to be here through the Michael addition. So their final product will look like this. So definitely try out some of these mechanisms on your own time. And let's go through another sort of last example for now. Treat this with LDA, and then second step we're going to add this Michael acceptor, okay, so you know that you're going to form an enolate here, and then this will come and it's going to attack this Michael acceptor, and you're going to get attack occurring specifically here. Okay, so you can imagine that you're going to get attack occurring here. Electrons will go up into the system like that. Okay, so maybe we'll just kind of go quickly through this mechanism. So you have your enolate, comes down, reacts here, and then you can push electron density through one of these esters. This will look like this enolate here, and then this will pick up a proton during the workup step. So just note that I added a workup step here, and then your final product will look like this. So I think by now you're all becoming quite good at the Michael reaction. And in these cases, it was fairly clear which product would be formed, and you didn't have a lot to worry about in terms of competing 1-2 direct addition. But what I'd like to do now is talk a little bit about hard versus soft inorganic synthesis and what that means and how we can apply that to the Michael reaction. Okay, so let's look at this electrophile here. You know you have two electrophilic sites. And for example, let's look at this one up here. You have a carbon and then an oxygen bond. So you know that oxygen is more electronegative. So I'm just going to draw a little dipole moment here showing that this is actually a more polarized electrophile, and this more polarized electrophile is more willing to accept something called a hard nucleophile. So we call this a hard electrophilic site. Hard electrophile, so more polarized. more willing to accept a hard nucleophile. So what would a hard nucleophile look like that we've been looking at the last lecture or two? So we've been dealing a lot with enolates. And enolates are very polarized, they're negatively charged, and these can be classified as hard nucleophiles. Hard nucleophiles have a greater charge-directed interaction, and they're typically very charged, and they're typically quite small. So if you wanted to get one to direct addition like an aldol reaction, enolates are a good choice. It's very charged, it's hard, and it's very likely going to react there. As we've learned, during this chapter, we want to actually get reaction occurring at this position here and do 1,4 conjugate addition. And so let's take a closer look at this site here. So this is also an electrophile, but you're going through a carbon-carbon bond. Although it is in conjugation with the carbonyl, we call this a soft electrophilic site. It's less polarized compared to the carbonyl. And therefore, soft electrophilic sites, or soft electrophiles, prefer to react with soft nucleophiles. What would a soft nucleophile look like? Over there, I've given you an example of a hard nucleophile. It's negatively charged, polarized, it's hard. The soft nucleophile counterpart of that would be the protonated form, which is not an enolate, but an enol. And you can see here that the enol is not polarized, it's not charged, and as a result, it's a much weaker nucleophile. This weaker nucleophile is therefore what we call a soft nucleophile. Not polarized, not charged. Weaker nucleophile, and this is often called a soft nucleophile. Okay? More willing to react with soft nucleophiles. So you can see here, perhaps if we're trying to do a conjugate addition through microreaction, it's probably maybe better to try to use a weaker, softer nucleophile so we don't get that competing 1,2 addition. All right, so let's take a closer look. And let's write this question here. How can we favor 1,4 addition? So let's take a look at this compound here, kind of similar to that ester that we looked at on that whiteboard there. And let's say we make a lithium enolate out of it. And then what we want to do is we want to react this with this compound here, all right, which is similar to that one. And then what we've learned is that, well, this is a lithium enolate, very good chance it's going to react here. So how do we promote or increase the chances that it's going to react here? Because we've already made a hard enolate. So what we can do is think back to what we learned with specific enol equivalents. And what we can do is say, well, can we convert this lithium enolate to a specific enol equivalent that would make it soft and that would make it less nucleophilic, but a weak nucleophile? So one thing that you have learned is that you can take lithium enolates and you can react these with TMS chloride to make something called silyl enol ethers. These are stable, they're shelf stable, and they're easier to work with. So if you treat this with TMS chloride, you'll generate your silyl enol ether. Silyl enol ethers, as you recall, are weak, they're soft nucleophiles, and if you actually take this compound and then react it with this, you're going to get no reaction. So how did we use silyl enol ethers and how did we activate them with their electrophile? Recall that we had to use something like titanium tetrachloride or tin tetrachloride to help activate it. So if we treat this with titanium tetrachloride, what you'll end up getting is this species here, and what we've identified is that this, I'll put a little star here, but this star corresponds to now a soft electrophilic site. So the soft electrophilic site will react very well with the silyl enol ether. So what I'll do is I'll have this come down and it's going to come attack. I'm going to have to use two boards here. Okay, it's going to react right at that carbon, and then you get electrons moving up as I'm showing you here. So what is that going to look like? You'll have your sort of your ester portion on the left. And your titanium is still negatively charged. Okay, so that's reacted. Your new carbon-carbon bond, it's always good to take a look at those. That is this one right here. It's a little crowded here, so I'll just, that's a methyl group, TMS group. Okay, new carbon-carbon bond. So now what's going to happen is that you have, this should be positively charged. You have this oxygen here that would really rather be neutral, pulling electron density away. So we have a very polarized bond here. This negative titanium, again, titanium is quite happy being neutral. So it's going to give up its electrons, transfer them to the negative oxygen, and then that's going to now react with the silicon and then push electron density to that oxygen to make it neutral. Okay, so we've gone this far. We have this neutral compound. This neutral compound will now come down during the workup step, and you'll pick up a proton from water. And then at this stage here, during the workup step, water also loves silicon because oxygen loves silicon. So you're going to get now the oxygen reacting here, pushing electrons and breaking that final oxygen-silicon bond because it's positively charged. And your final product will look like this. And this will be your major product, and you have really avoided the competing 1,2 direct addition product, taking advantage of the soft electrophilic site and using a silyl enol ether as a specific enol equivalent. What other specific enol equivalent have you seen that is very useful, that you think would be very useful for microreactions? Okay, so think about that while I erase this board here. Specific enol equivalents are good. What is another soft nucleophile, do you think, that you've seen before? Well, if you thought of enamines, then you are correct, because enamines are neutral nucleophiles, and because they're neutral, they are weaker compared to enolates and aza-enolates, and therefore these would make good candidates for the microreaction. So enamines as enolate equivalents. So if we treat this compound, for example, with this cyclic secondary amine, you know right away that this is the recipe to create an enamine. So that will look like this. And this is what we call a soft nucleophile. Specifically, we can call this a soft nucleophile, or because we're dealing with the microreaction, we can call this a soft Michael donor. So the soft Michael donor when we react it with this electrophile here, that's your hard electrophilic site. This is your soft electrophilic site. So this will come down and it will react at this position here, so we can get 1,4 conjugate addition. Okay, then you push electrons up into that carbonyl, then this will come down during the water workup step that you already learned about. This should have a hydrogen there. Yeah, don't forget this is a hydrogen, since we're dealing with an aldehyde. And what are we going to get? We're going to get this compound here, this is your iminium compound, right? So we need to go back to that aldehyde. So again, water, acid will hydrolyze that back. You know the mechanism, right? So that's, therefore, this will be your final product. Okay, so enamines are also a great choice because they are softer and weaker. And the last question I have today before we end the lecture is one last predict the product question. Okay, so in this question here, by now you can see that we're going to make an enamine. This will become your nucleophile. This will react at this soft electrophilic site. And then let's think about later what will happen with the water workup step. So let's go through the first two examples. So this will react here. So you can imagine you have this chain off of this carbon, and then we'll go back and hydrolyze that imine back to the starting ketone. So you'll get something that will look like this. And when you take water and acid, another thing that can happen is that you now have a situation here where you can actually undergo 1, 2, 3, 4, 5, 6, an intramolecular aldol type of reaction. So you can imagine that under appropriate circumstances, you could form an enol on this side, and because these are acidic, 1, 2, 3, 4, 5, 6, and then you could dehydrate water. So this is also known as the Robinson annulation, and what you'll end up generating is this compound here, okay? And if you don't believe me, go through that mechanism step on your own. So conclusions from this portion, I just want to highlight that enamines and silent enol ethers offer the best for 1,4 conjugate addition. If possible, when you're doing these Michael reactions, try not to use lithium enolates. They work if you're forming like a 5-membered ring or the choice is really clear, but if you have a lithium enolate, then you will typically get a competing reaction. Okay, so if possible, avoid hard Michael donors like Enolates. Okay, so that's it. That's it for today. See you soon for chapter or for lecture 26.